invite you to Karen to start with the webinar.
Alrighty, thanks, Cesar. Okay, everyone, good morning, good afternoon, wherever you're joining from. Today, we'll talk about how we can use AI and EDEM to aid in machine design. A little bit of background. My name is Charanjot Sibichin. I am part of the EDEM technical team, and I'm based out of Minneapolis, Minnesota, in the US. And I generally work with consultancy work, sales opportunities with potential customers, and also looking at customers' interest in EDEM and the viability, and explain what EDEM is capable of doing and how far it can go. In the context of machine design, system simulation can definitely help us with the design process of any machine, like shown in this case. So today we'll talk about in the context of wheel loaders. So as you can see, there's forces on these bell cranks, these linkages, and the booms of this wheel loader, and those forces can be calculated using simulations. And how those forces are calculated is also, it is a function also of the interaction of this, let's say, bucket with the particles or the material that it is lifting. So in that context, you would need something for simulating particle interactions with the bucket and also the particle interactions with each other. In that respect, DEM or discrete element simulations come very handy, and there is a tool which can do DEM simulations. But for now, the main part is that DEM is something that is necessary to do particle and particle equipment interactions, and DEM is inherently a very computationally expensive solver. So it will take a very long time to do this. And also, as you can see in this particular case, these particles are or this motion is being actuated by these actuators that you can see here, and the forces on this, it's a combination of this dynamics of the body and the interaction forces from these particles. So there is a co-simulation, or let's say a coupling of this body with a DEM solver, not just with a DEM solver, which does interaction of particles, but also with a multi-body dynamics solver. So DEM is inherently very computationally expensive, but adding another solver, MBD, will make it computationally even more expensive. So the challenge is, how can AI help in speeding up the simulations by replacing this DEM with, let's say, a reduced order model? This is the example that we'd be looking at today. So we have flexible bodies. Well, let's say this boom is a flexible body. We have these hydraulic actuators, and this whole, let's say, whole wheel loader is a multi-body model in MotionSolve, or MotionSolve is the multi-body dynamic solver. And this is the bulk material that this wheel loader is interacting with. Just to introduce EDEM in general, so what EDEM is, it is a way of simulating particulate materials at the individual particle scale. So let's say you have soil or powders or sand or anything like that can be simulated using EDEM, and EDEM is powered by, as you can see here, discrete element method. And discrete element method is something that helps simulate such particle to particle interactions, and also any particle to, let's say, equipment interactions. And what EDEM is mainly used for is the investigation of process mechanics. So you can understand what is happening at a macro level and also what is happening at micro scales between each particles, which is not always possible experimentally to understand also. And finally, EDEM can help in virtual prototyping and optimization as well. Just moving quickly to the motion solution. So how do you do motions in, let's say, Altair solutions? You would first of all assemble your CAD, build your model, and then you will solve the model in, let's say, a multi-body dynamic solver, which in this case is MotionSolve. You will evaluate those results again with a tool called as HyperWorks. And then finally, you can do optimization study or improve upon your design using HyperStudy or so. But we will not focus on all of this. We'll mainly focus on MotionSolve today, which helps in just this multi-body dynamic simulation. So next, I want to focus on romAI, or ROM stands for Reduced Order Model, and AI is artificial intelligence, as most of you must know. So romAI is an application which is based on artificial intelligence, and it allows you to start from, let's say, data, and this data can come from simulations, or it can come from individual tests that you have. Then you identify a model. Let's say you have a even dynamic model, or even static model can be represented. You need to identify what model you have, and then you would create a digital twin, or for let's say a digital twin, for an IoT application. Or in this particular case for today, you'll create a reduced order model, which is a real-time simulator, and that can be used to speed up an optimization process. So, and finally, you can also do a lot of control and everything with it. But for today's context, we'll focus on the reduced order model aspect of it. So this is just the general workflow of how you would use AI and EDEM for speeding up your simulations. So you would have your DEM or EDEM simulations first, and you would create a bunch of training data out of it, and then use romAI and create a reduced order model. And then with that reduced order model, this reduced order model is a representation of this DEM model now. And this reduced order model can be coupled with, let's say, a multi-body dynamic solver, and you don't need to couple EDEM, or let's say the DEM solver, with the multi-body dynamic solver, and that speeds up your simulations a lot. Just why romAI though? So romAI is Altair romAI, I should say. It democratizes the access to AI, because AI inherently, I mean, is understood as a very complex, math algorithms and whatnot. But romAI democratizes that access, and then there's only certain inputs that you need to put in, and then you are also able to use AI for your particular application. In this case, the machine design applications. Next, I want to briefly touch upon Twin Activate, what Twin Activate does. So Twin Activate is a system integration platform, and it has a very modern modeling environment, and that can handle scripts with, let's say, with different syntax, OML, Python, Modelica, and so forth. And then it also has blocks of different nature, signal-based blocks, Modelica for, again, physics-based, and you have Spice also for electronics. But anyway, why am I talking about Twin Activate is because you can use Twin Activate for this co-simulation. So let's say here you would create your block, which is your reduced order model block, and then Twin Activate can connect your reduced order modeling block with a physical simulation, which in this case is a multi-body dynamic simulation. So it allows a very seamless co-simulation environment. And you can do transition from, let's say, 0D to 3D. All kinds of simulations can be done on Twin Activate also, and it is also the same platform. Next, just showing how to generate this, let's say, ROM or this reduced order model. So initially you would need something called as training data with EDEM, and you will, let's say, run 10 different scenarios, and this is the simulation that we want to couple with motion solve. So what you do is you create different scenarios with different Z bucket displacements, X bucket displacements, and then run all of those. And then once you have all of those, then you export the inputs and outputs from EDEM, and then create a reduced order model within romAI director. And then you load the generated romAI block, and then run the romAI thing. Let me show you, for instance, how all of this works. This is an EDEM simulation, which is complete for now, but you can, so here I have defined this bulk material, or the material which it is interacting, which in this case is rock. So you have this rock material, you can specify the density of the material, you can specify the shear modulus of the material. you also specify the equipment material. So in this case, whatever equipment material you have, steel or iron or whatever, you can specify that material properties in here. And finally, you would have these geometries which you would create in a CAD and import in EDEM. And then you can also specify the motion. You would specify the motion of this bucket. Let's say it's going from here, it's lifting this and then turning over here, which means that there's a rotation, and then the bucket is being lifted. So all of this happens within EDEM, and then after the simulation is run, this is what it would look like. Okay. So as you can see, it will take the particles and then it will lift the particles. So you don't need the rest of the wheel loader, because the rest of the wheel loader is not interacting with the particles. You only need the bucket for now. And now, once you have this simulation done, let's say this is for the first scenario or the first case, and then we will export the data, which will eventually be imported for for the reduced order model. You export the data. What are the data that we are exporting? First of all, we're exporting the positions, x positions, then the z positions. Then I'm also exporting the velocities, x and z again, and then I should export the orientation of the bucket. And then, so this is why am I exporting all of this? So you need certain amount of inputs for the romAI model, which in this case, the inputs would be the x position, the z position, the motion, the velocities of the bucket, the orientation of the bucket, and the time. And the output that you get out of this simulation, or probably which you want to get out of the coupled motion solve romAI simulation, is the forces on the bucket, the torque on the bucket, and the mass of the particles inside the bucket. So this is the example I'm going with. So for that, these are all my inputs, and then in the bottom I have my outputs. So I have the total mass inside the bucket, I have the torque, and then I have the forces also. So these are all the inputs and outputs that I have, that I am exporting, that I can import later on for my reduced order model. If I can show you, this is the Excel sheet gets exported for, let's say, one particular simulation. And then when I do it 10 different times for 10 different cases, I would have an Excel sheet. Well, I would have to merge all the Excel sheet, but then I would have data of all of them together. So in here, as you can see, the time goes to 4.5. So this is the end of the first simulation, and I have all of these values for 10 for the first simulation, the x position, z position, the velocities, the orientation, and the angular velocity. And then finally, I have the forces also. And so after that, once the first simulation is completed, then my second simulation results are here. So you need to merge all of those results one after the other 10 different times so that you can import it into romAI. So I have done 10 different simulations and I have imported all of them here. So that was the easy bit, or probably that is something that some of you may already be familiar with, how you can export data from EDEM. But now let's move into seeing how to create this reduced order model using this data that we have generated out of EDEM, and how we can couple that reduced order model with motion solve. So you open Twin Activate. So Altair Twin Activate is, as I said, is the system integration platform, and romAI is a system block within Twin Activate. I click on romAI director, it is executing call, it will create the interface for me, and then I can show you how easy it is to set up a reduced order model. This romAI works similar to any other simulation tool that you must be familiar with. It has a pre-processor, it has a processor, and it has a post-processor. So for pre-processor, I will import my data, and so this is the merged data for training. I have all these individual data files also, and this is the merged data. So I open this, And then I can visualize the data, how it looks like. So I have 10 different segments, and X position, I can see how the data looks like for all of this, and I can verify if this looks correct. I can visualize the velocity, I can visualize the orientation, and so forth. Let's say I have these forces also, which I can look at and make sure that my inputs are all correct to build the reduced order model. So here you can see there's a lot of noise in here, so you can also add some cutoff or probably add a filter, and then that would filter your data so that you have a more smoother response, which will be used for your reduced order model creation. Then romAI would not use the original, let's say, unfiltered data, and you can add another filter for the Z force also if it is too noisy. But for now, I mean, I just wanted to show that it is possible. I don't want to use any. I will leave them as is. What I want to emphasize here is that you can visualize all your data here and make sure that everything is correct. And you can also, if required, add a filter to your data. But for me, everything looks good, no filter. And now I will export it to the builder. So now in this builder, I have a lot of things to do. So first of all, I need to specify what are my inputs for this reduced order model and what are the outputs. This is a dynamic system. This is not a static system. So with that in mind, you would not have time as one of the inputs for your model, because then you are, let's say, almost cheating, because you don't want to say that at this particular time I want so and so to happen. You want all of the rest of the variables to determine what will happen with, let's say, the forces in this case. So you will say that your X, Z velocities, orientations, and angular velocities are the inputs. And for those positions and the velocities, what are the appropriate outputs, which in this case, what forces do I get for this particular combination of X, Z position, and velocities and angular velocities, and so on. I would have mass as one of the outputs also. Again, because this is a dynamic system, you would have to also specify what is the state variable. So if you're familiar with system theory, so the number of state variables in a system is equal to the minimum number of variables required to define the exact position or state of the system. So in this case, mass is the only state of mass is the one state in this system. One might argue that you could have force as the state, as one of the states of the system also, but in this case you would not use that, because this force is dependent on this mass also. So because of that, if you choose two states, that would be incorrect. You would only choose one particular state in this case, which is the mass. So also, to understand what is the state, you can also think of it something as a memory effect. So it will depend. So whatever this particular state of the system is, it is dependent on the previous state of the system also. So it has a memory effect throughout the whole simulation or throughout the whole time that we are analyzing. I will just start the simulation, and then we can talk about what these individual parameters mean, because this will take some time. So I will build my reduced order model here. So it is executing callback. Just thinking about it. I need to select my output folder path. All right, so I'll select this folder, and then I'll call it reduced order model motion solve EDEM, and then I'll start again. Okay, so it is doing things here. So in that, while it's doing it, I will talk about what each of these things, options mean. So first of all is the model type. Linear and non-linear, fairly self-explanatory. For this particular case, you have a very complex system, so you would choose a non-linear model type to create a reduced order model. And then for the activation function, so traditionally, okay, little background. romAI is built on neural networks. Everything behind romAI is, Yeah, whatever happens inside of romAI is all based on neural networks. So traditionally, the activation function used for romAI or for neural networks for was a sigmoid function, and then then there was a new activation function after that, which was a hyperbolic tan. So hyperbolic tan is a more symmetric function, and then you would also get a better model accuracy with the hyperbolic tan. We have that particular function. We don't have the sigmoid function. And then also there is another function called as ReLU, which is rectified linear unit activation function, and that is a even better activation function. You can get better model accuracy also with it, and then you also eliminate the issues of having vanishing gradients with this particular activation function. So basically, well, in simple terms, ReLU is generally used when you have a lot of discontinuity, let's say in gradients of your function, of the function that you're trying to optimize or get a reduced order model for. But tanh is generally used if you have, let's say, more continuous functions or continuous in gradients, let's say function, then you can also use tanh. ReLU is also a little bit faster than tanh, so that is also something to think about. Hidden layers is the number of layers that you have in between, let's say, input and output for your neural network. So in this case, you have 3 hidden layers. And then here you specify how many neurons you have in each of the hidden layers. So it is generally good practice to have all of these neuron numbers in each of the layers to be the same, but you don't necessarily have to do it. Just a note on these layers. In most engineering problems, you only need 2 or 3 layers, and in this case, I'm just using 3 layers, but you can sometimes get away with 2 layers also. I've never seen anybody use 10 layers, but maybe that is a case that can happen. Epochs is the number of iterations that you want to do in your system. So basically, with any AI model, what happens is estimate a weight function and a bias, a weight and bias values, and based on that weight and biases, you would create, let's say, you would calculate a cost function. And the idea of the whole AI model is to reduce the cost function. And how many iterations do you want to run to reduce the cost function as much as possible? So that is what epochs is. So you would choose how many epochs you want or how many iterations you want. The more epochs you have, the more convergent your cost function will get. And this is the test split ratio, which means that how much of this test data, which in this case we had 10 segments, so we'll say 9 of them are used for training and 1 is used for testing. All of this is done, and now we've reached a test loss of 0.005764, which is good enough. That's the loss metrics. If you go to accuracy check, you have R-square value of 0.9113, which is a good value, but I would not recommend you look at this value for any useful purposes, at least for dynamic systems. R-square value is a very good metric for static systems, but not necessarily for dynamic systems. And finally, you can how the way you measure if your model is good or not is go to time simulation, and you can see the data set is what we gave as an input, and romAI is what the reducer model came with as an output. So you can see we have good match with the reducer model and data set with not as much error, with an acceptable 10% error. Yeah, mass is also again within 10% error, as you can see here. Alrighty, so with this done, we have a reduced order model that we can use for our coupled simulation now. So how we do that is you go to activate, and then you go to co-simulation, and then get, let's say, our motion solve signals. So motion solve is the multi-body dynamics solver. Let me open motion solve and show you also. Motion solve is a multi-body dynamics solver, and in motion solve, or in the solver, you have to create a subsystem or a reduced order model subsystem for it to know that it is wanting to run a reduced order model coupled simulation. So while it is opening, I'll probably move on with the signal viewers or let's say romAI. So I'll import this romAI model, and here I will say what is the ROM folder that I want to use. So this is the folder that I want to, this is the model I want to use. I hit apply, okay. And in here, you specify the motion solve model, which in this case, I'll use this model. It will take some time to load. So I, just looking at the Q&A, at which point of the bucket of the forces and torque calculated, it's calculated at the center of mass of the bucket. Okay, it's taking way too long, but what happened? Okay, hit apply. Okay, so now we have this motion solve model. So this motion solve model, or this multi-body dynamics solver, it requires forces as inputs, and the outputs that it gives is the bucket displacements, or what is the bucket position at certain times, what is the bucket velocity, the bucket angle. So these are the outputs from the motion solve or the multi-body dynamics solver, and the inputs it require is the forces. But for our reduced order model, it is the exact opposite. So what we do is we just connect both these here. So the bucket displacements from the motion solve, or the values from the bucket displacement from motion solve, goes to the reduced order model, let's say, and then the reduced order model will give forces, and those forces needs to be sent back to this multi-body dynamics solver, and based on this updated forces, it will give new bucket displacements, and those displacements are again sent to the reduced order model, and then it is sent back to calculate the torques and the forces, and also the mass. But mass is not an input that is required by the motion solve model. So once this is done, you can pretty much run the model, and the way you run it is from here. But let me set the total final time to 7, and I can run the model. But before that, I also want to, let's say, have signal. Yep. See this file, CSV file. So what I want to import is a CSV file, and I have done a coupled EDEM simulation, not with romAI, coupled DEM multi-body dynamics simulation, and I'll just bring in the CSV file from that particular simulation, let's say. This one goes from CSV. Oh yeah, this one. Sorry. If I delete this. So I did this couple simulation, and then I bring this, and I bring all this forces in here. Why I'm doing this is just to compare if the motion solve simulation is giving correct results, or just to compare how the romAI motion solve coupling does compared to EDEM motion solve coupling. And then I also add a scope in here. Sorry. Need two inputs. And then I can choose to have this, and then this goes here. So now I have forces. This is the force coming from the actual simulation, from the actual EDEM motion solve coupling, and this is the force coming from the coupled simulation. So you can just visualize the forces here also. Okay, and then you run the simulation, and then it will go running. Okay, so I will probably stop sharing, and I will take any questions now.
Thanks very much, Jorin.
Yes, the position and speed also at the center of mass of the bucket. So all of these forces, positions, and velocities, all of them are calculated for the bucket itself, because that's the only part that is interacting with the particles. So everything is calculated at the center of mass. So why we are doing all of this is just because the coupling, or the romAI, runs much faster than a DEM simulation. So a coupling, so you don't need to have a coupling of EDEM with motion solve to be able to use romAI. So if you have any simulation which is just particle simulation, and then you want to use AI, or probably use reduced order model for that particular particle based simulation, you're able to do that with romAI also.
Okay, so thank you very much, everyone, for attending this webinar. Thank you very much, Jerry. And then we can leave it till here.
All right. Thanks, everybody. Bye. Take care.
Bye, everyone.